If you have done all of the practice problems for orbital diagrams and electron configurations, you've seen a good amount of repetition. We fill that first level before the next. We fill the 2s sublevel before the 2p. There's repetition with it. There's a pattern. And with enough practice, it becomes pretty natural. But the tedious thing about it is that it's always the same thing. So if we looked at something like lead with its 82 electrons, we have to write 1s, 2s, 2p, et cetera, et cetera, et cetera, all the way up till we get to our level 6, where it fills with that 6p. Remember, the location on the periodic table connects to which is the last sublevel or which are the last orbitals to fill. Lead is right here. It's in row 6 in the p block. So that's our indication that we're going to fill all the way up until we get to level 6 to the p sublevel. And we can even connect that it is the second one in that section. If I shift slightly here, thallium is the first one, lead is the next, which is our indication that the last electrons to fill would be 6p2. The reason that I say that this is tedious and not just repetitive is that if everything starts off the same way, why do we always have to start with that same thing? If we know that lead, for example, ends as 6p2, why can't we just write 6p2? The reason we can't jump ahead to that is if we only write 6p2, there is some gray area. 6p2 means that I have 2 electrons that are in level 6 in the p sublevel. Normally, we would expect that that means everything is full up to there, but from flame tests, from just the Bohr model in general and our understanding of electrons, everything that we are writing and drawing is a ground state electron configuration, meaning the electrons are in the lowest possible and most stable electron configurations. But by gaining energy from heat, from light, or from electricity, or lots of sources, those electrons can be excited to a higher state. If we just wrote 6p2, there would be a gray area as to, are we talking about lead, which ends as 6p2, or are we talking about helium? Helium has 2 electrons. Its ground state electron configuration is 1s2, but it is possible for it to gain energy and one or both of those electrons to jump up to any level above level 1. They could go to 2, 3, 4, 5, or 6, and they could end in an S, P, D, or F sublevel. So by just saying 6p2, we are leaving that open to interpretation. So what we need to say is, I'm ending at 6p2, but what's coming before it? Or I do have everything up to and including 6p2. The format we use in order to do that is called a noble gas notation. We know the last column on the periodic table from helium down to radon are the noble gases. They have full levels and full sublevels. They have filled their S's and their P sublevels. As a result, they are unusually stable as they're maximizing attractions while minimizing repulsions, which we'll talk about even more in trends. So the electrons that maybe neon or xenon have in those full levels are not very reactive and therefore not significant in describing the properties of the element other than it's non-reactive. So what we do is a shorthand basically saying for a noble gas, and I use the same example throughout, which you already figured out. So thinking about phosphorus, it has slightly more electrons than neon. Neon is the noble gas, not necessarily closest, but the closest one before phosphorus. So we always go to the noble gas before it. Neon has level 1s or 1 full, all of level 2 with the S and the P full. So when I write the symbol Ne inside of brackets, that's the same way as saying I have the same 10 electrons for neon in the same 10 places that neon has them. The 1s, the 2s, and the 2p are all full. Those are full, those are stable, those are unlikely to participate in any reactions or any exchanges of electrons. So for phosphorus, these 10 electrons are likely to be kind of off limits. So then with the noble gas notation, I'm focusing on the electrons that phosphorus has that are most significant in describing its properties. It has electrons in level 3. Those are the ones that are likely to be involved in bonding, either covalent or ionic. Those are the ones that would be lost or gained in an ionic bond or shared in a covalent bond. So the noble gas notation uses a noble gas to talk about all of the full levels that come before it, while highlighting the level that is partially full and the level that is most likely to be reactive. Often on the AP exam, they ask for electron configurations, and it is up to you which version you like to write. The only thing that's important is if they ask for a complete electron configuration, that you do the full one starting at 1s. If they specify it needs to be noble gas, you must use this version. So we've got a couple practice there to show how we can significantly shorten lead, and francium with its 87 electrons, how we can write that much, much shorter.